Okay, as I said in the last class, we are going to discuss the homework problems first. So who will present first?
Ma'am, can I start?
Yes, you can start.
Can you see my screen, ma'am?
Yes. So each person will have roughly 5 minutes to explain what he or she has done. So do that first.
Okay, ma'am. So this is the first question. First
Yes,
of
I
all,
understand.
uh,
Understand. Okay.
so
Then
you understood the step, right? E of
yes,
x y
yes,
definition. Then
yes.
I considered this PDF of y
Okay.
into this problem. Then PDF of y problem is whatever is there in this into fy PDF of y dy. But we know that joint x given y, PDF of x given y is joint PDF by PDF of y. Then I substitute this value in one, that in exy. Then I would get this integral. Then I substituted this part in this two equation,
Okay, I
second equation.
understood.
Fine.
Scroll down.
Then so
All
then I
of you.
got
Okay. Scroll down. Fine.
then I got this way. Finally, the marginal PDF of x is this part. So I have written x of x dx, which is nothing but exx.
Next.
Next problem, we need to prove that we know what we need to prove, that E of I is A into E of x plus B. I have taken some normal matrix of A with some elements in it, B and X, just to show that finally Ax plus B would be in this way. Now if I consider some m by n and n by 1 matrix, the final matrix would be this way. When I multiply Ax plus B, I would get this matrix, and when I apply the expectation to expectation of y is equal to expectation of ax plus b, I would get this way, right? Then e of constant into x1, some random variable, would be a into e of x1 plus a12 into e of x2 and so on, plus e of b1. But e of some constant is a constant, so it will be b1 only. Then it is something, this is something similar to a matrix elements of a multiplied to e of x.
But that you
So
can do in vector form also, right? So whatever you are saying that A11, A12, they are all deterministic terms, right? That's why
yes,
you
ma'am.
are applying expectation on only on the random terms. So
Mm-hmm.
that you can do even in the vector form, right? Then you don't have to do this matrix
This
multiplication.
much I didn't know, but for my understanding, I just
Okay,
get this.
fine. Next.
This is proved. Now I have to prove that covariance of y is a covariance A transpose. So just I'll substitute in, this is a covariance formula for y minus e. Then I substituted the value of y and e of y, whatever I got in this. Then it will be e of ax plus b minus this into ax plus b minus transpose. So then I would get ax plus b. Then when I bring the transpose inside, it will be something like this.
Okay, I understood.
BB
Next.
will be cancelled and I would get this way.
Okay, fine.
So
Next,
yeah,
please. Fine.
then this will be the covariance matrix of X. Next question, this is given, E of XY transpose equal to 0 is given. I need to show E of X transpose Y is 0. So again, I did the same thing, like I expanded the matrices, then I multiplied, found estimation, expectation for each value and element in the matrix. Then by saying this, we understand that each element in this matrix is 0. Now when I consider x transpose y, this is the matrix which I got, and when I apply expectation, since each element in this matrix is 0, in this matrix also each element would be 0, ex1
Yes.
y1.
Okay.
Yeah,
Next.
so this is 0. Fine. Now
Okay.
fourth problem, I need to prove that semi-definite matrix would satisfy this condition. I took x as some random vector, a is a fixed vector, and y as this. Now I considered a random variable y as you say transpose into x minus
Which
e of
one
x.
is 1 minute? Which one is random? Which one? A is
A
deterministic.
is fixed deterministic, and x bar and y bar
Okay.
are random variables. I
Mm.
considered a matrix of, a random variable y in this manner, in this fashion.
Okay.
Now expectation of y square is always positive. Whatever values we have
Yes.
in y, it is positive. So y square
Very
is
good.
y
Yes.
trans.
Yes.
Right now, when I consider expectation of y, I substituted y values over here. Y as this one, y transpose as this one. A transpose into x minus. Then when I take the transpose inside, I would get A transpose x minus E of x into transpose of this. Then constant would come outside A transpose into this is nothing but the covariance of x. Now for particular whatever covariance matrix I will take, it would be A transpose kxx into A. Since x is some
fine. I understood. Okay, next.
Last problem I didn't do, ma'am, because of exams and other exams and assignments. So I have done
but
only
you should
this.
do that.
I'll do, ma'am, definitely. I'll do
okay,
that.
next. Who will
That's
explain
it.
next?
Thank you.
Who will explain next? Whoever wants
Yes,
to
ma'am.
explain. Yes.
Yes, ma'am. Can I explain?
Yes.
One second, ma'am. Ma'am, is it visible?
It's difficult to read, but okay.
Ma'am, this is the first question.
I understood. Scroll down.
Okay, ma'am. Ma'am, this is the second question. I applied expectation on y.
Okay,
so
next.
using, then again, I for second question, second part, I just expand the term, and I got the A into kxx A transpose. So that was the proof. Ma'am, can I explain this?
That I understood. Okay, next.
Okay, ma'am. And this is the third question. Since expectation of x y transpose.
Okay, I know the problem. So you just show me what you have done.
So
okay, next. Scroll down.
Ma'am, just I compare
diagonal elements at 0, so that from there
yes,
you are concluding. Okay, fine. Next.
Yes, ma'am. This is the fourth question. Expect covariance formula is given there.
Okay, next. What you have done?
So this A transpose x minus mu x is a random variable. This is a number actually. X is a random vector, and this S will be a random variable. So it's this is the ES square is the variance of a random variable S. So I'm assuming sigma S square is the variance of that ES square. That will be always greater than or equal to 0. This is the proof of.
Then after that.
Ma'am, this is the first.
Okay, so you have done all the computations step by step.
Yes, ma'am.
Oh, okay.
This is
you don't have to explain. I can see. Okay, next. Just scroll down.
Finally, I got.
No. Answer is not correct. 22 points. No. How can you get 22.67? You just see the magnitudes of y. They are so small, and how can you get x so large?
Ma'am, I'm using all sigma and mu from the previous equation.
No. You have made some computation mistakes. Next, for the WLS. WLS also you got the same. Scroll down.
I got 2.836.
Then you should get similar estimates. From there, you should have found out what you did wrong. Which one is wrong? This one is okay.
Ma'am, I will check again.
MMSA is not correct. You have made some calculation mistakes. Okay, fine. Next.
Okay. No, this is there are 6 questions.
Fine. Next.
Okay, thank you, ma'am.
Murali or Nilay, who will explain next?
Ma'am, I can show.
Please.
Ma'am, I tried doing, I was able to do only one problem.
You cannot say that you are able to. You did not spend time. And all of you have attempted the first problem the same way. It's substituting fx given y, and then fine. Then?
Yes, ma'am. This was the only problem I was able to solve.
Okay, fine. Next. Murali?
Yes, ma'am. Sharing the screen. Ma'am, I could try 3
Okay, show me then. After
So
that,
this is
okay, at least he has done it in a different way, substituting x. One minute. So fxy, okay, fine. At least he has done it in a little different way. Okay, fine. After that, so why did you write this step? 1 minute, 1 minute. I am not done it. So this you have written xy. Say what did you write? Theta. No, theta is not the standard notation for PDF. It is
no,
f.
ma'am. I have not written theta anywhere.
What is that notation? The theta given x, theta x comma y. Is that theta or f? What did you write for PDF? Is that f?
Yes, ma'am. That's F.
It appears to be theta. Okay, theta. So, okay. So how do you write the next step from that line? From this line to next line?
Ma'am,
Where your
so
cursor is?
yeah, integration of minus infinity to infinity. This is joint PDF.
Okay.
So we can write it as fx of x.
Okay, fine. Next. Okay. Next.
So this
How
one I
did you do
actually
it?
forgot to include the plus b. Actually, it will be cancelled inside.
Yes, but you need to include. Otherwise, the expression is not correct, right? It will not be. Yeah, b will cancel out, but still you should. Otherwise, expectation of y is wrong, right? Okay.
Yeah, ma'am.
Then.
And this is the third problem.
So these three problems you have tried.
Yes, ma'am.
And what did you write? Greater than equal to 0. What is that you have written?
Because it has valid. It is valid, and there is a square term, so it has to be greater than 0.
There is a square. 1 minute. What did you write? A transpose. Okay, all transpose. No, the final expression that you wrote. Okay, transpose A. See, A is a vector. Okay, don't think that A is a scalar. A is a vector. A has to be a vector, right? Otherwise,
Yes.
does not make sense.
Yes, ma'am.
Okay. Fine.
Okay.
Okay, I have Shujit's solution. I'll share the screen and then Shujit can explain, okay?
Okay.
Yes. Shujit.
Yes, ma'am.
So I
So first,
understand what you have done here. So all of you have approached this way. You are just substituting this one. Why don't you write whatever Murali did? Why don't you write this one? That also you can expand and then whatever he did the same way you can proceed. Okay.
okay.
So for this one, what you did, you applied, but you should write why you are applying the expectation operator on X. That should be
Okay.
written. This one, again for this one, you do not need to do all these computations. You just substitute for Y. Okay, if you substitute for Y,
Okay.
and then you apply on the expectation operator only on the random terms. So that way you do not have to do that you are doing.
Yes,
See,
ma'am. So
at
just
this point, you could have. I think it is a little detailed. I mean, there is a shortcut approach for this one.
okay.
Okay, so what you have done here, you are just considering the diagonal terms. Okay.
Yes, ma'am.
But why are you showing 3 by 3? It's n cross n, right? So you should have some dot and then you should show
Yes,
it.
yes,
Do
yes,
not
ma'am.
write a 3 by 3 matrix and say it is an n by n matrix.
Okay.
That's not
Okay.
correct. But this one, what have you done? Quickly tell me.
Ma'am, just A is the vector. We are taking the transpose of this matrix form and then just multiply it, these three matrix. Then I will get finally a square terms, a square expectation of this, and this means every term it will be positive because there is no negative signs here.
How can you
And
say
that,
every time is positive x to x1? X to x1 will not be positive. It's not necessary. That
but
x to x1.
expectation, but we are taking the expectation of higher term.
So,
um,
if you take expectation of x1 square, it is positive.
Positive, yes,
But
ma'am.
x to x1, you cannot guarantee to be positive. You cannot. Have you understood what others have done?
Yes, ma'am.
So that's how you should approach it.
Okay.
You cannot guarantee that this is positive. You can also not guarantee that when you subtract the second term, this one, the result will be positive. That also you have a negative term here, right? So you cannot guarantee that it will be positive. So unless you approach that way, starting with that expectation of a scalar being positive or greater than equal to 0. See, one more thing you should keep in mind. It will be equal to 0 only when x is deterministic. If
Yes,
x
ma'am.
is random, it will not be equal to 0. So equality holds only for a deterministic term. Okay. So for
Okay.
a random term, it will be, I'm telling everyone, random term, it will be always greater than 0. That scalar you have shown in the, I think two of you have shown, right? Expectation of the scalar, I mean, E of, you have shown, right? Y square, expectation of y square greater than equal to 0. That equality sign holds only when y is deterministic. For random variable, it's not 0. Moreover, another thing that you should, I don't know whether you probably have considered, those who showed the right approach, for them I'm saying. Okay, so Shujit, you understand, right, where you went
Yeah,
wrong? So this is wrong. You cannot say
okay,
that
ma'am.
this is positive, and then you cannot
Okay.
also show that this is positive unless you do it in a different. Okay. So I think we discussed the homework problems, but I'll show you the and however, okay, you did that calculation. I saw your calculation. Yes, it appears to be correct. And see, you are asked to find the same unknown x using different methods. A quick cross-check would be to see whether you are getting similar values of x. It cannot be that different methods will give you completely different values. So the moment you see that one method, from one method you got 22 and from another method you got 2, that means one of them is wrong. Since you do not know the correct answer, you have to suspect one of them. And the one which is deviated, much deviated from y values, should be the wrong one. Because you just look at the model you need to consider. Y is equal to x plus v. And you see the variance of v. You cannot have 22. You see the variance of v and you see the magnitudes of y. So the one which is giving 22 is wrong. So this is how you can easily find out which one is wrong. Krishna, you understood what I said?
Yes, ma'am.
Okay. So I'll quickly do that problem. I will need to show that the covariance matrix is positive semi-infinite. So we need to show that A transpose Kxx A is always greater than equal to 0 for all A, and A is deterministic. Okay, so we know X is a random vector and Kxx is expectation of just consider a random variable A transpose X. Now, dimension of A and X should be compatible so that we can do this A transpose X, right? Therefore, Y is actually a scalar. Right? Let's say mu of Y is its mean, so Y minus this is greater than or equal to 0. Now this equality sign holds only when you have a deterministic Y. For any random Y, it will be greater than 0. Okay. Now this term we can also write this way. We know Y is equal to A transpose X, right? So this we can write Y minus mu Y transpose now we can substitute for Y and mu Y, right? What is mu Y? Mu Y is actually expectation of A transpose X, right? Or instead of taking transpose here, we can also take, since Y is a scalar, we can also take the transpose here. And this is possible only when Y is a scalar. If Y had been a vector, we could not have done this. Now we can substitute for Y and mu Y, right? Now we know that Y is A transpose X and mu Y is actually A transpose expectation of X. So basically from the first term, A transpose will come outside. A transpose X minus mu X. And similarly for the second term, we have X minus mu X. A transpose A. Because we need to transpose the second term. Now we know that the X term is nothing but the covariance matrix, right? And the expectation operator has to be applied only on the deterministic term. So we have to take A outside and finally we could prove that okay. Any question? If you do not have any question, we'll continue with the discussion of the MMSE estimator. Do you have any question? No question? Okay, now the syllabus for Friday's test is up to today's class. So whatever we discuss in the, now is also included in the test. Okay. So last time we were discussing the orthogonality principle, and then we would like to derive the linear MMSE estimator, linear minimum mean square error estimator, with a batch of measurements. Since we are using a batch of measurements, we call it a batch estimate. And we consider n measurements, capital N measurements. Each measurement is of dimension m cross 1, right? And we have this nonlinear functions. We are interested in estimating this unknown quantity x. X itself is a random vector to be generic, and it's of dimension n cross 1. And then we have this noise term, which is of compatible dimension. Since we have n cross 1 measurement, n is also of dimension n cross 1. And this way we have n measurements. Each measurement is of dimension n cross 1, and we have n capital N measurements. And we stack all the measurements together in this capital Y vector. We will not use different notations because these are standard notations. So let's stick to standard notations, not use any non-standard notations. Generally, we use Y to represent the measurements and X to represent the unknown quantity. Stacking all the measurements, we have nm cross 1 vector, and then let's assume that capital X also changes. Therefore, we have to estimate capital N times small n cross 1 vectors. And then here we have the corresponding noise vector. Now we are interested in an estimate which is a linear function of the measurement y. So to have a linear function of y, to start with, we apply this constraint. We say that C is a matrix, deterministic matrix. But unknown. We do not know C. We want to find an estimate of x hat such that it is related to y through C. And our objective here is to apply the orthogonality principle because we want it to have an important property of the MMSE, minimum mean square error estimator. We want to apply the orthogonality principle and find x hat. But at the same time, we will use this constant also. So let me write here. We want x hat right. Now x is of dimension this and y is of dimension. So what will be the dimension of C? C is a metric. Can you tell me what the dimension of C will be?
Nn by nm.
So it's a large matrix. Now we want to apply the orthogonality principle. So using the orthogonality principle, we have, so we know that the estimation error is actually x minus x hat. So this is the estimation error, and we know that this is orthogonal to any function of y. Now we can pick any function of y. So let's pick this one because we want a linear estimate. This is a zero matrix. Since it is it's orthogonal, the estimation error is orthogonal to any function of y. We have just pick y itself, so that we have a linear function at the end. So everything is linear. We do not want to introduce non-linearity because it will distort the PDF, and we need to, and there is a higher chance of introducing more errors, because this n term we have in the measurement we have the noise, right? The moment you introduce non-linearity, there is a higher chance that you will also have higher order n terms, because non-linearity means you have to take a non-linear function of y, and y has noise included in it. So nonlinear y means you also have nonlinear n and higher order n terms that can increase the error. Okay, because n is an error, n is basically an error. So if you increase n, that means you have higher error in the final estimate. So that's why we do not want non-linearity to the extent possible. One reason is that you are distorting the PDF the moment you introduce nonlinearity. Another thing is that there is a higher chance that you have higher order n, so that will increase error. So to the extent possible, we do not want any nonlinearity. And this is why we are trying to have a linear MMSE estimate, because MMSE does not guarantee that the estimate is always a linear function of y. Okay. Now our objective is to find C, and we want to find C in such a way that this orthogonality principle holds. So let's substitute for x hat. Now, although I am writing only 0, it is not a scalar term. You just need to have a 0 matrix of compatible dimension. Now we need to rearrange the terms. So we have x, y transpose. From the first term we have x, y transpose, and we apply the expectation operator. And then from the second term we have C will come out because it is deterministic, y, y transpose. Right? Now, we want to find C. And then taking this term on the right side, we have this one, right? So what is C? C is basically this one, right? Now here, I missed one thing. See, this is a nonlinear function, right? H need not be linear. So if it is a nonlinear function, we need to linearize it with some guess, right? So that linearization part is missing. So we need to incorporate that. So let's quickly do that. Let's call this dash x dash and y dash. So here we have dash. Okay, and what is x dash? X dash is actually x minus x. It's a tilde. So x tilde is the initial guess of x such that okay, expectation of x is equal to expectation of x tilde. This condition holds. Just like the WLS estimator, we are starting with some initial guess and we are going to linearize the nonlinear function about that initial guess. What is y hat? Y dash. Y dash is y minus y tilde. And what is y tilde? Y tilde is actually this. Okay. So instead of having x and y, we need to have x dash and y dash. And final expression of c will also be changed accordingly. Okay. We know that x dash is x minus x tilde. Ideally, we should write delta x, but writing delta x and delta y everywhere now would be difficult. That's why I'm using x dash and y dash. Okay, so let's linearize the nonlinear equation. We have y is equal to h of x plus m, and we need to do Taylor series. Expansion. I am taking only the first order terms. Right, so in the place of this one, we can write where H is the Jacobian of H. Capital H is the Jacobian matrix. Of the nonlinear function H. Small h is not a single function. It has to be a set of functions, right? Otherwise, we cannot have this equation. This equation. So it is actually a set of nonlinear functions. And we already discussed the expression of Jacobian matrix in the context of WLS system. I am not writing it here. Now, using this linearized version of the nonlinear measurements, we are going to find those expectation terms. We have some expectation terms, right, in the expression of C. So this way we will not be able to evaluate C. We will not be able to find C, right? We need to find these expectation terms. So let's find the first one, expectation of x dash y dash transpose. So what is the expectation of x dash? So we know x dash is x minus x tilde. We also know that expectation of x is equal to expectation of x tilde. X tilde is the initial guess of x. So what is the expectation of x dash? What is the expectation of x dash?
0.
0. Okay. So let's say x dash transpose. This is equal to p. Okay. Now in this case, since this is a linear MMSE estimator and it gives importance to both prior information and measurements, we need to know p. Okay. Unlike the WLS estimator where p need not be known because in the final expression of the estimation error covariance p is eliminated. Here we need to know p. Okay. We can treat this as sort of error x minus x tilde. You want to estimate x minus x tilde, and this one is nothing but the error covariance, initial error covariance. Okay. So if we substitute for y dash, we have x dash plus n transpose, right? Now x and n, x dash and n, or x and n, they are independent. X and n are independent. Okay, because n is measurement error or measurement noise. X is the quantity we want to estimate. They are generated by two completely different processes. So it is realistic to assume that x and n are independent. They do not depend on one another. So given n, we cannot say anything about x. Given x, we cannot say anything about n. And also n is Gaussian distributed of 0 mean, n is Gaussian distributed of 0 mean and covariance W. Okay. Now here again we have two terms, x dash transpose h transpose, right? And for the second term, so what do you think the second term will be? For the first term we can write pH transpose. How about the second term?
Since the
it should be
mean.
0.
Yes,
It is 0 because n is of 0 mean, right?
yes,
so the expectation of x dash y dash transpose is actually pH transpose. Next, we need to find the expectation of y dash transpose because we found this term. We need to find this term, right? So we need to find expectation of y dash transpose. Again, we need to use the linearized equation of y and apply the expectation operator on individual terms. So you have hx dash n dash hx dash okay. Now see, when we do the multiplication, we'll have one term which depends only on x dash and we'll have another term which depends only on n dash. In between, we'll get two terms where we have x dash and n dash, right? And we have already seen that this term is actually 0 because x dash and n are independent and the mean of n is 0. So simply saying that this term is 0 because x dash and n are 0. X dash and n are independent is not enough. You also need to say that the noise n is of 0 mean. Otherwise, you cannot discard this term. Okay. So those terms which require the expectation of this one will be eliminated, and we'll have only the x dash terms and another term involving only n dash, right? So again here h will come out and we have h transpose because we have transpose in the second term, and then we have expectation of n dash transpose, right? And then we also get this x dash times n dash transpose, which we know that will be 0. Similarly, we have n dash x dash transpose, again this will be 0. This is why we have only 2 terms instead of 4 terms, because the other 2 terms have 0 expectation. We know this one, this is P. So we have H, PH transpose plus W. Now we need to substitute this expression here. So we got the expression of x dash y dash transpose. We also got the expectation of y dash transpose. You can use that in the expression of C. We know that the first term is PH transpose. I just now derive the second term. I need to take the inverse of that. HPH transpose plus W whole inverse. So this is the expression of C matrix. Okay. So just like any other estimator, we are interested in finding the estimation error, mean and covariance, right? So what is the estimation error? Let's denote that as delta x. So delta x is actually x minus x hat. X dash is x minus x tilde. So this is estimation error. Okay, we will use the standard notation which we used for other estimators, epsilon. So epsilon is the estimation error. Right. Now again, we take the expectation of this to know if it is an unbiased estimator or not. So that means we have expectation of x minus expectation of x hat, right? We know x hat is C times y dash, right? So all we need to find is the expectation of y dash. What is the expectation of y dash? What do you think? What is the expectation of y dash? What do you think will be the expectation of y dash?
Ma'am, it will be h into expectation of x dash.
What is the expectation of x dash? What is the expectation of x dash?
0. Then total E of y dash is 0.
It is 0. It is written here, right? We have picked the guess in such a way that its expectation is the same as the actual expectation. Therefore, expectation of x dash is 0, and hence from this equation we can say that expectation of y dash is also equal to 0. So incorporating that here we get sorry, I have to find the expectation of x hat. This is x hat prime, right? X hat dash. So this one is cy prime, right? So what is x hat? X hat must be x tilde plus this one. You just see we considered x dash to linearize the nonlinear equation, right? And then we found this one, an estimate of x dash hat. But we are actually interested in this one, correct? Right? So we have to use this equation. So we know that x dash is equal to x minus x tilde. So x is actually x dash plus x tilde. And we got an estimate of x dash, correct? So to get x, the estimate, corresponding estimate of x, we need to add x tilde, right? Therefore here we also require the expectation of x tilde, because we are interested in finding the expectation of x hat. So x hat will be, the expectation of x hat will be actually expectation of x tilde and expectation of x hat dash, right? And this is expectation of x hat dash. And we also need to include expectation of x tilde. And from our guess, we know that expectation of x is equal to expectation of x tilde. So here, in the place of expectation of x tilde, we can write expectation of x, right? Is this clear to you? Did you understand why I wrote expectation of x tilde and expectation of x? Have you understood this? Yes or no? Did not understand? You did not understand? Yes or no, you can say at least, right? Have you understood or not?
Understood, ma'am.
So from this, we know the first and third term will cancel and the second term has zero expectation. Therefore, expectation of epsilon is 0, which implies that it is an unbiased estimate. So tomorrow we are going to find the estimation error covariance, okay, and then we'll look at the Kalman filter equations. Now you need to do the following. You need to apply the linear MMSE estimator to that example problem. That y is equal to x plus b, simple problem we are considering. For that problem, you need to have a linear MMSE estimate. Okay, so you need to find P, you need to find H, everything you need to find properly, and then find the estimate of X. So for the other two estimators, I told you what you need to do, how you need to find H, how you need to find W, everything I told you. So using that knowledge and the expression of the linear MMSE estimator, you need to find the estimate of X for that example problem. Okay. That's it for today.